Tonight is June the 29th, 2021, and I've got so many things I've been thinking about lately that I want to share with you guys. Oh, but I seem to have a hard time getting really focused. Well, anyway, what I want to do, here's a stereo SCT 300B, goes great, 7 watts. Here's a really classy little, I think I need to turn it down here right now. Williamson uses a BO13 Chicago transformer. Those BO series ones, they make a great big one like this. And I remember a fellow back here, when I first came out to El Paso, made stereo amplifier with 2 mono blocks, power supply in each one. It was awesome. He could back the nails out of the wall. He ran 6146s in it, push-pull. They recommended 6550s, but he changed it to the 6146s. It was very powerful. Anyway, I think what might be fun is to carefully examine and document the harmonic profiles between, say, an SCT, a tube amp, and let me turn this guy around, and I got a big solid-state Mac amp right there. Can you see that guy right there? It's a 2100, 105 watts per channel. Works great, etc. And because I'm convinced, let's go back around here. I'm convinced that the sound of an amplifier is in its harmonic profile. Odd harmonics, even harmonics, who knows? Who knows what anybody likes? Seems like the preference is even, and I'm not going to dispute it. But it's interesting that the SCT amplifier has all the harmonics in it in a nice straight descending order. And a push-pull amplifier usually have the second harmonic suppressed more than the third. Maybe that's why people don't like them, because they don't like those odd harmonics. Never thought about it that way until right now. But it's interesting that we go back to SCT amplifiers, and then, well, anyway, here's just a glimpse. This one's not running right now, I don't think. And you've got terrible glare on it right now. Let's see where that glare is. Let's turn this off. Did that help anything? Nope. Oh, no, it's not glare. Not really. That's the little white things in the middle. Okay. Anyway, I got 2 of these FFT type programs up, and you see I moved the monitor over to the workbench. That I have been enjoying ever since I did it. I should have done that years ago. Another thing that I don't have a really good handle on is transformers. Can you imagine? Transformers, how hard can it be? Well, you know how hard it can be. I just got in a little driver transformer today. This little guy right here. It's a driver transformer out of a DX100 ham radio transmitter. It uses a 12BY7 driving a pair of 1625s as a modulator. I've had one of these in a Heathkit. I've heard them on the air not so long ago. They sound great. Anyway, it's a nice little audio transformer. Well, I've been playing with this thing about the turns ratio and the impedance ratio, and we know all that, don't we? Yeah. And you know, some of the old books talk about the primary to 1/2 the secondary. Well, this thing right here has kicked me around tonight because I estimated about 20K grid to grid, and maybe 10K over here. And you know what? That's exactly what I get. If I put 20K on here, the series resistance, the ESR, as some people know it nowadays, right there's 10K. Perfect. But when you start joggling that ratio around with this little driver transformer, it just goes haywire. And so does the frequency response. I don't know if there's any anything extra in that thing or not. Maybe they got a capacitor or resistor or something in there. They don't show it in the schematic. But it's very frequency dependent. At a kilohertz, it does everything you think it's supposed to do. Anyway, those things, as much as I think I understand them sometimes, there's always one that wants to jump out there and bite you. Let me show you something I picked up here not too long ago. I really wasn't able to determine exactly what the thing was worth until tonight. But actually, I've been evaluating this thing for quite some time. It's a little Hewlett-Packard amplifier. Amplifies 20 or 40 dB from 1 kilohertz to 150 megahertz. Well, it does. It works at 100 at a kilohertz, and I've tested at 14.2 megahertz. I haven't actually gone to 150, but I'm sure it works. And it's actually quite accurate. If you do square wave testing on it, it's not so hot. Right here, it's got horrible low frequency attenuation. That doesn't matter. This is not like a problem. It's not broke. But sine wave amplification is quite good. But this is at what, 14.25 megahertz. If you run it down to 1 kilohertz, it's got a very low frequency roll off. Well, that's high frequency roll off on the leading edge. Anyway, the darn thing works. I don't know how many years old it is. Now this little signal generator right here, I've been measuring it lately, and here's what I did. I tried an experiment, and maybe I'll try it again. It just didn't turn out exactly at all the way I thought it would. I wanted to put, you know how we put a square wave into the input when we do square wave testing? And we measure the output and we look at the leading edge and we play around with the ringing at the corner a little bit, and then we say, oh, that looks great. And we do it at 1 kilohertz and 10 kilohertz, and if it does great there, it is great. Because, you know, to pass a square wave with a pretty good leading edge takes a frequency response at least 10 times the fundamental. So if it'll pass 10 kilohertz square wave and look good, and it's saying it's got a bandwidth at least up to 100 kilohertz. Now this little generator right here is a vacuum tube, and it will generate low voltage, like a volt, I think. No, down to millivolt. Anyway, with leading edges much faster than a nanosecond, about a half a nanosecond. I say much faster, but better than a nanosecond. And this little guy right here is a rare bird. I know we got wires in the way. It's a calibrator, and it works. Okay, back to the first subject though. But when it comes to square waves, a perfect square wave has only the fundamental and the odd harmonics, and any dissymmetry between the two half cycles will show up as even order harmonics. So I thought, well, if I put a square wave into an amplifier, and I did this on the push-pull amp, and I was wanting to see if the amplifier itself was actually generating any second order harmonics, and I figured that by examining the second order harmonics of a square wave going into it, I would have a very sensitive indicator if the amplifier is indeed generating second harmonics, and I did not find that to be true. This little push-pull amplifier, just showing you right here, it did not, the best I can remember, it did not generate any second harmonics. It kind of surprised me. I don't remember what the results were on this. I'll have to run it again. I bet this one does. And I'm beginning to think that second harmonic is somehow kind of important. As much energy as was spent many years ago developing push-pull amplifier to get rid of that second harmonic. Look at this guy right here. This is a beauty. I do not recommend buying one of these. You know, everybody that has high-end audio equipment built in the 70s, 80s, and probably even 90s, maybe up to 2000, I don't know the number, if it met the specs on this guy right here, it was laboratory grade. This thing still works. It's something that I trust, but only for stuff in the kilohertz range do I find it really useful, because these little FFT programs are they're so much faster. And looking at low frequencies, it'll show 20 hertz, but it may take 20 minutes for that trace to go from left to right to show you what a 20 hertz signal looks like. So it is brutally time consuming. Let's see. I wonder if I got this other one running. I'll show you though how quite amazing they really are. Let's see if I can make this one run. Yeah, right there. Okay, take a look at that one. Look at this closely. Whoops. We got the fundamental. Second harmonic's a little higher than the third. And then we got a fourth down there that you just barely can see. Let me get my finger in front of it. The fourth harmonic is right down there. See, we just barely can see that one. This one has a noise floor of, well, it has 10 graduations on it, so it'd be 100 dB, but it's only rated at 90 dB, and it does a darn good job all the way down to 90, that's for sure. But with that harmonic profile in mind, let's look over at the little FFT one. And we see the same thing, except a little bit more. See, we see the second a little higher than the third, and then the fourth is way down. And then we see all of those other goofy little harmonics out there. What's that? Second, third, fourth, 5, 6, 7, 8, and 9. I think it's real. It's pretty amazing, isn't it? For a program that's free. It doesn't give you that sharper display if you get it for free. No, this one is definitely not free. The other one, this one right here. Yeah, you have to pay as much as $100 to get everything with it. And you get the real sharp displays. But there again, there it is. Looks like the other one, maybe it's just because we had the noise floor lower. The other one, right in here, we actually saw better. But the other one's a much more expensive program. The oscilloscope on something like this is actually not too bad. Let's see, we take the spectrum analyzer. We stop it by starting the oscilloscope, I guess, is how we do it. No. Okay, come on. We stop it, and then we can go to oscilloscope, and there it is. Is it running? No. There, it's running. That's not bad, huh? Okay, I'm going to show you something here in a minute. That. Stretch it out. I like it. Okay. Now, I hope I can hook this up quickly. I'm not sure if I can or not. But what I want to show you is when you do put a square wave. Now I don't have the stuff set up. It'll take me so long to do this. I'd want to stop the camera, do it, and start again. When you do square wave testing on an amplifier, on this oscilloscope over here, on a 350 megahertz oscilloscope, you will get the truth, this guy right here, and it can come out just beautiful, just beautiful. Make it good as you want. But the square wave display on this thing right here is absolutely horrible, and you cannot believe it when you put in a square wave. Let's see, maybe I can even, well, there's a square wave, but I got to run it back around into it, well, maybe, no. What in thunderation am I looking at anyway? I don't even know what signal I'm looking at. Oh, I'm looking at the SCT amplifier. Okay, well, let's do this. Okay, here's out of there. Let's put in a square wave. I can do this without too much trouble. I didn't realize we were looking at the SCT. I thought I was looking at that other one. let's see if we start the. I think we got to go down here to square wave generator, and then turn it on. Something hooked up right. We got to turn up the gain. Maybe that's it. Something simple. Yes. There it is. There it is. Okay. I'm having a pretty hard time syncing on that. I'm not quite sure why. I've got a lot of 60 hertz hum on there. I've got something loose here. This is not what I want to show you, but if you look at the tops to the bottom, you see how bad they are. If you look over here, look at this right here. This is an error condition. This is a tech error condition, but look how square it's trying to turn out. I got 60 hertz coming in here big time from somewhere. Coming in from here. Why in the world am I seeing all that? Holy moly. That should be a virtually perfect square wave. There's our harmonics. Darn. This is a terrible example. But anyway, this one will show just an absolutely beautiful square wave, not modulated by 60 hertz or whatever it is that we're mixing with it. And just keep trying to figure out what I'm mixing with it. And this one over here, comes up, got a lot of squiggly lines in it. It's like the sampling rate is way too low. Lots of ringing right here, and then it goes down. Lots of ringing, comes up lots. So, the moral of that story is, if you're going to do square wave testing, even though this thing's got a square wave generator, don't rely on this oscilloscope for what it looks like, because it is not accurate. The scope's good for a sine wave. I guess that's about it. Well, I'm just modulating the heck out of that with something. Oh, do I have both amplifiers? Yeah, I got both amplifiers on. No, I just got it switched to the right, which is this one. This is what I do all night, trying to figure out. This thing must have pulled loose from the. Nope. Well, we won't worry about that right now. Okay. Well, I'll quit for the moment. I think it's 20 minutes till 3 a.m. I stay up really late. I've been playing with that little HP amplifier, just making sure it works right, and it does. I'm quite amazed with it. It seemed like there was something else I wanted to talk about right here for a moment, but I don't remember it. Well, this is about a I don't know, a 15 or 20 minute shop talk. So if you guys, this is what I would like to see. This is what I like to see on YouTube. I'd love to go to you guys' shop, sit there and talk about all your stuff. Stay safe, my friends, and thanks for watching. Well, I got some high voltage wire right here. It's called, if you look up Packard 440 wire, this is spark plug wire. Brand new spark plug wire, made in USA. I'm going to use that in my transmitters instead of meter lead wire. But when you buy spark plug wire, you got to make sure that you buy copper core. Otherwise, if you get what's called radio resistant wire, it won't work. It's got a real flexible kind of a silicone type conductor in it or something. It's pretty high resistance, and it stops your radio from popping, especially your old AM radio. And if you run this on your spark plugs, I used to do this, you won't be able to hardly hear your AM radio, much less a ham radio.